In this video, we're going to talk about z-scores and the normal curve. I'm drawing a normal curve here. I'm trying to make it as symmetrical as possible, meaning that the right side and the left side look the same. Another characteristic of the mean, or excuse me, of the normal curve is that the mean is in the center of the distribution. Specifically, the mean, the median, and the mode are all the same value if a curve is perfectly normal. Now here I've tried to draw another normal curve. And what I've done here is I've drawn a line down, and this line is cutting this curve into two pieces. This smaller piece on the right here, we are going to call the tail. And the larger piece on the left, we're going to call a body. These two terms, tail and body, are terms that you're going to have to learn how to apply to different normal curves so that you can do the homework assignments that are going to be coming up. So the thing to remember here is that whenever you cut a curve into two pieces, the smaller of the two pieces we're going to call the tail, and the larger of the two pieces we're going to call the body. So let's just do it again to show you what I mean. We have a normal curve. I've cut it. I've created two pieces. This time, the larger piece is on the right. So we're going to call that the body. And the smaller piece is on the left this time. And so now we're going to call that the tail. Again, this is how you're going to be applying these terms in future assignments. The larger piece of a normal curve is going to be called the body, and the smaller piece is going to be called the tail. Another important characteristic of the normal curve is that the area under the curve is equal to 1. So the entire area under the curve is equal to 1. So if I were to split the curve into two pieces, in this case the larger piece is on the right, so we're going to call that the body, and the smaller piece is over here on the left, and we're going to call that the tail. If we were to take the area under, or in the tail portion, so all of this area, if we were to take that area and add it to the area in the body, we should get 1. The body plus the tail will always give you 1. Okay. Now that we understand the shape, the very specific shape of a normal curve, it's important to know that many different variables that we work with on a normal basis form a normal curve. For example, if I were to measure people's height, people's weight, people's score on some standardized test, many of these variables will naturally form a normal curve. And that's why understanding the properties of a normal curve is pretty important. So we're going to talk a little bit more about the properties of a normal curve here. So here I've tried to draw another normal curve. It's important to recognize that when I'm drawing this, what I'm really drawing is a frequency histogram. That's what this little f means. It's a frequency. The higher the line is, as I go up this line, follow this curve, the higher that line gets, the more common that score is. That's why up here at the top, we have the highest distance between this line, the top line, the curved line, and the bottom line. that means that there's a lot of scores in there. Okay, and as we go down, the scores get less and less and less. Okay, so there's very few scores down here, and there's a lot of scores, or I should say over here, and there's a lot of scores here because the curve is high at that point. Okay, now what I've got, I've put in a little number line here. The shape, that little number line, I should say, is the number line that's going to be true for all normal curves. The center of the number line, the center of the curve, is mu. That's the symbol for the mean of a population. And then the next number to the right of that is the mu plus 1 standard deviation. The next symbol to the right of that is the mu plus 2 standard deviations, and so on. So to give this some concrete numbers, if the mean of this distribution was 50 and the standard deviation was 5, we could create a standard raw score number line below our universal number line in red. And that's what I've done here. The mu is 50. Mu plus 5 is 55. Mu plus 2 standard deviations is 60. Mu plus 3 standard deviations is 65. And then we can go down as well on the other side. Mu minus 1 standard deviation is 45. Minus 2 standard deviations is 40. Minus 3 standard deviations is 35. Now, the normal curve has even more specific characteristics, and that is that the area under the curve between 1 standard deviation above the mean and 1 standard deviation below the mean is approximately 68% of the entire curve. So in other words, 68% of all scores are between 45 and 55. 68% is between the score of 45 and 55, or between 1 standard deviation below the mean and 1 standard deviation above the mean. Furthermore, the area between 2 standard deviations below the mean and 2 standard deviations above the mean is equal to approximately 95% of the entire curve. So you can see most scores are really tucked in the middle. More than half are between 1 standard deviation below and 1 standard deviation above. And almost more than 95% are between 2 standard deviations below and above. And then we can go out one more, and we can see that virtually all of the scores are going to be between -3 standard deviations and +3 standard deviations. So this gives you a sense of how common scores are. A score of 35 in this distribution is going to be very rare. A score of 65 is going to be equally rare. A score of 50 is going to be pretty common. A score of 55 is not rare, but it's less common than 50. Same thing for 45. Now, where the cut line is between a rare score and a common score, we'll come to that. We'll talk about that in a future activity. We're going to give you a cut line. We're going to give you a specific definition for what constitutes a rare score. But right now, you should just have an understanding of the normal curve having a very specific shape. And when I say very specific, it follows all of these characteristics that I've lined out. Okay. Now we're going to do a little bit of an example here. So we've got a normal curve, and it has a mean of 20. It has a standard deviation of 10. So I can take these values and place them in the appropriate spot on this normal curve. Since the mu is 20, I can put that in the center. Then one step up from that is going to be 20 plus 10, which is 30. One step up from that is 40. One step up from that is 50, and then I can do the same thing going the other way. So now I have a raw score number line under this normal curve. And it's all based on, the reason why I can fill those specific values in is because I know the population standard deviation and the population mean. Now, what I'm interested in doing here, and this is why we're interested in using z-scores, is z-scores allow us to take advantage of the known properties of this normal curve. So if I have a score of 15 on a given measurement, and I want to know how well I did relative to other people on this measurement, first thing I want to do is locate my score in the normal distribution. The normal distribution is right there on the number line. I've noticed where 15 is, and I want to know, how well did I do? How many people did I score better than if I scored 15? If the mean is 20 and the standard deviation is 10, I'm going to be able to use z-scores to figure out how well I did relative to other people. So I need to use this z-score formula. The z-score formula is z equals the score of 15 minus the mu of 20 divided by the standard deviation of 10. And if I work that out, I'm going to get negative 0.5 for the z-score. Now what does that mean? That means negative, I scored less than the mean, and 0.5 means that I scored half a standard deviation below the mean. Now, I'm interested in knowing what proportion of the population did I score higher than. So I'm interested in the area under the curve in this shaded region. Now the way I'm going to figure out that area is I'm going to use a table in the back of your book. It's Appendix A in the back of the book. So what you need to do is you need to look up in that table, under the z-score column in that table, 0.5. Now I know the z-score is negative 0.5, but the z table doesn't have negative values. So what you have to do is you have to look up 0.5. And then when you get to that 0.5, there's going to be two columns across from that 0.5. One of those columns is going to be labeled tail, and one of those columns is going to be labeled body. Well, when you look at this shaded area, is it a tail or is it a body? Is it less than half the curve? If it is, then it's a tail. And so yes, this is a tail. So you go to 0.5 in that Appendix A. Under the tail column, you're going to find the value 0.3085. That means that approximately 31% of the people did worse than I did on this measurement. They scored lower than I did if my score was 15. Okay, going to give you a chance to do this. Here is another curve with the mean and standard deviation of 20 and 10, respectively. And the first what I want to do is show you how we can convert the raw score number line that we have on the bottom into an actual z-score number line. So I'm going to take the mean and plug it into this equation. So how could I translate a raw score of 20 into a z-score? So I would take 20, which is the raw score, minus 20, which is the mean, divided by the standard deviation, and I would get 0. So I can put 0 under 20. Basically what I've just done is I've translated a raw score of 20 into a z-score. These are like two languages. I'm translating from the raw score of 20 to the z-score language, which is 0. And I can do the same thing for 30. 30 for x minus 20 would give me 10. Negative 30 minus 20 would give me 10. And then 10 divided by 10 would give me 1. And then 40 minus 20 would give me 20, divided by 10 would give me 2. And I can do that for 50. And I can do it for 10. And I can do it for 0. And I can do it for negative 10. So the blue number line represents the z-score number line. The orange number line represents the raw score number line. Now what I'd like you to do is find the z-score that corresponds to a raw score of 35. So go ahead and press pause on the video and see if you can figure out the z-score if the raw score is 35. Okay, so hopefully you have performed the equation and have found the z-score. Here's what I came up with. So I always write the formula first, substitute in the values that I need, 35 for x, 20 for the mean, 10 for the standard deviation, and that's going to give me a z-score of 1.5. Well, 35 on the raw score number line is located here, right? That's where 35 is. And so it makes sense that 1.5 in z-score language is going to be right underneath that, right in between a z-score of 1 and 2, just like 35 is right between the raw scores of 30 and 40. Now what I'm interested in this question is how many people did I score better than if my score was 35? So I'm interested in the shaded area. Is the shaded area a body or a tail? It's a body. And so we want to go to Appendix A. We want to look up a z-score of 1.5. And then under the body column, we want to find out what proportion of the normal curve is to the left of a z-score of 1.5. If we do that, we'll find that the area is equal to 0.9332. In other words, a little bit more than 93% of the people are giving a score less than 35. So these are the types of things that you're going to be doing in today's activity. Specifically, you're going to be working with raw scores, converting them into z-scores, and then finding the probability of any given z-score. This should help you do activity 4-1.